Hello, everyone. Welcome to the talk about the price of dynamic memory in C and C++. And tonight we're going to talk about how much does it cost in terms of performance of you using dynamic memory in C, both in C and C++. How much time does it need for? How much time does it take for you to use it, and what are the ways to fix and to make your programs run faster? So let's move on to the slides. So I'm Ivica Bogosavljevic. I'm an application performance specialist, and I focus on application performance improvements. So these are techniques used to make your C and C++ program run faster. And the way this is achieved, there are several ways how this is achieved. You can use better algorithms, and most people do that, or you can better use the underlying hardware, better use the standard library, programming language, and so on. I also write for the Johnny Software Lab website. It's my personal blog, so the link is in the footer, and also work as a performance consultant. So first, an introduction about the types of programs that exist here and how they use your memory. So in the early days of development, so most of the programming was done in huge large buffers, and this is still the way how it's done now. For example, image, audio, and video processing algorithms typically will allocate a few large buffers and iterate through those as arrays or vectors or matrices, and then iterate through them. Tonight we won't be talking about this kind of problems because most of the programs that are written now there are much more intensive in terms of their memory usage and the way they use memory. And these kind of programs are interesting to us. For example, if your program uses fast random access data structures such as trees or hash maps, and many programs nowadays do, it will allocate many small memory chunks. It will ask many small memory chunks from the system allocator. If your C++ uses pointers to store data, such as raw pointers, unique pointers, shared pointers, it will also make many calls to the system allocator. Classes that have pointers, such as classes which as data members have pointers to other classes, will also allocate additional, will put a large stress on the system, on the system allocator, on the system allocator, and on the memory subsystem, on the CPU's memory subsystem. So all these programs that allocate many memory chunks, allocate memory, access memory in a random fashion, can suffer from performance degradation. Okay. So if your program is allocating a lot of memory and it is slow, you might ask yourself, why is that? And there are two reasons. The first reason is if your program is allocating a lot of chunks, the performance of malloc and free, or in C++, these are new and delete, can be a bottleneck. So if you profile your program to see which functions are slow, you will see in your program, in the output of your profile, you will see that malloc or new takes about 10 or 15% of the time, which is quite a lot of time just to do allocation, memory allocation, and the allocation. On the other hand, there is a problem of memory access. If your program is accessing a data structure in a random access fashion, these are tree, hash maps, objects allocated on heap, performance can suffer because of the data cache misses. So I assume that you at least have some idea of what are data cache misses, and later I will talk about data cache in more details. So if you profile this kind of programs in the profiler, you will see that the function is slow, but you won't have a clear reason why is that. So in that case, you need to focus to use specialized tools, so not a regular profiles, but specialized tools that can debug data cache misses or slowdowns due to data cache. In Linux world, you have a perf profiler that can do that. You have cache grind, which can also do that. We'll talk about data caches a bit later. So the first part of the talk is the performance of memory allocation. So let's first give a short introduction about memory allocations. So what is a system allocator and how the allocation process looks like. So system allocator is an implementation of malloc and free functions that allow your program to allocate and deallocate memory on demand. So these, please do not confuse system allocator with the STL allocator. STL allocators are something else, and we'll talk about them because they're really useful for our story. Internally, system allocators ask for a large block of memory from the operating system and then serves your program with smaller chunks. So they take smaller chunks of memory out of this big block and then assign it to you. Your program then uses this chunk of memory to keep its data. In order to make your program run fast, allocation algorithms must be really fast. So these are performance critical stuff, and we will talk about that a little bit later. So I don't know if you see my pointer. So this is an example of a large memory chunk that has been taken from the operating system, and these fields that are in green are, just a second. Yeah. Okay. So these fields that are in green are the fields that are taken by your program, that your program is currently using. So this one and this one and this one. The fields in white are part of your memory that is available, and the memory allocator can, when your program asks for memory from the memory allocator, the memory allocator will return those blocks that are available. This is one way of keeping the allocators can keep the list of available blocks. Not the only one. There are much more advanced ways, but this is just an example of how it might be done. So the biggest problem of memory allocation and the allocation is the problem of memory fragmentation. To fragment means to break something, and this is like breaking large blocks into pieces. Now, I guess most of people have heard about memory fragmentation. I'm just going to give you a short example, a short description and an example here. So, as your program runs, it allocates and deallocates memory. As time passes, it gets more and more difficult to find an empty slot of the right size. This is the problem of memory fragmentation. So as your program is running, it gets more and more difficult, and it takes more and more time to allocate and deallocate memory. So as the time progresses, new and free and delete take more and more time. And you can see here in the image, this is a block of memory which the allocator owns. And you can see here that this thing that is in green is the memory that's allocated, and these small chunks in white is the memory that is free. So if your program would ask for a memory of, for example, of 6 of these small blocks, the allocator would certainly have to go through some kind of data structure to find the block of appropriate size. This is the problem of memory fragmentation. It can be seen many times. If you have a program that runs for a few hours, you'll see that, for example, when we did the TV box development, we had a problem that at the beginning the TV box, so there was a test that took 24 hours. At the beginning, the channel would switch every 2 seconds, but as the time progressed, it would get slower and slower. And after full 24 hours, it will take 10 seconds to switch it, to change to another channel. So fragmentation is a serious problem for long-running programs and systems, because it causes slowdowns. So new and delete take longer, and because it causes allocation failures. It might happen that your program has enough free memory. For example, it has 2 megabytes of memory, but it doesn't have it as a single block. So this thing cannot be allocated. Okay, moving on. There are basically 3 reasons why allocation and the allocation is slow, and here they're presented in the order of importance. The first reason is that you're doing many calls to the allocator, new and delete, calling malloc and renew and delete a lot. So if there is a way to decrease it, if there is a way to decrease this number, this will have a great effect on your program's performance. The second thing is memory fragmentation that we just covered. And the third one is that your program is using an inefficient implementation of malloc and free. The system allocator is not efficient enough. If you fix any of the three above reasons, this will make allocation and allocation in your program faster. Often, if you decrease the number of calls to malloc and free, automatically this means less memory fragmentation and your program can work faster and can work faster for a long time. Okay, any questions until this point?
Nothing just yet. Keep going.
Okay, I hope you find this interesting. So moving on. One of the solutions, and there are many solutions to memory fragmentation, and we'll cover some of them. One of them is not to use vectors of pointers. There are programming practices that inevitably lead to many calls to malloc and free. And I think the worst offender in terms of performance is vector of pointers. So this is std vector of object pointer, std vector of unique pointer to object, and so on. So each element for each element of the array, they'll be called to the allocator. And additionally, there is a bad performance when you access those data structures due to poor data locality. What does this mean? Is you have in your vector you have neighboring pointers at location 0, 1, 2, 3, but these pointers don't necessarily point to the neighboring blocks of memory. And if this is not the case, and this can happen, you will get there is a huge penalty in performance that we'll talk about it later. So there are some alternatives. So one of the big motivation to use pointers of vector is a polymorphism in C++, but luckily there are alternatives. One of the alternatives, if you need to use polymorphism in your program, is to have separate vectors per type. So you have if you have 4 types: rectangles, triangles, circles, and so on. You'll have one vector for triangles, one vector for rectangles, one vector for circles. This approach is really good because it has an excellent data locality, and the compiler can do a lot of optimization there. There is the boost has one container called polycontainer. The bad thing about this approach is that the elements in the container cannot be sorted, cannot be all. How should I say? You cannot put the elements of the structure in any order you like. So there is a limit in the ordering. All objects of one type have to go first, then the objects of second type, and the objects of third type. So this boosts polycontainer, and there is also this multi-vector that I wrote as part of one of the articles. They will allow you to write really concise and nice code using C++ template mechanism that's also fast, and it doesn't use any runtime polymorphism. All polymorphism is done at compile time. The second possibility is to use the vector of variant. This is a good alternative if you need a container where you want to put specific element at a specific place. So this is one of the possibilities. There is something also I wrote for another article. It's called polymorphic vector or polymorphic array. It's really similar to the std variant array, but there is a slight difference. So if you are in a need, you should have a look at if you're in need, you need performance on your vector of pointers, you should definitely have a look at these different containers. All of these approaches decrease the number of calls to malloc and free. Instead of having malloc for each element of the array, you have just malloc for a vector, large block of memory that holds all the objects. This approach also decreases memory fragmentation. Now, questions? Okay, moving on. Oh, okay. Another solution to decrease memory fragmentation and increase the speed of allocation and free is to use STL allocators. Now, system allocators are implementation of malloc and free, and STL allocators are tied to your specific data structure. So fast access data structures that are based on trees and hash maps, such as std map, std list, std unordered map, std set, and so on, allocate a lot of small memory chunks from the system allocator, and this increases fragmentation and slows down your program. Alternative is to use a dedicated STL allocator for your data structure. So the STL allocator you configure your STL allocator, you should write it yourself, and there's also some solution that you can find online. But the main idea is to use, for your data structure, to use a dedicated block of memory. When you allocate from a dedicated block of memory, when your data structure gets destroyed, you can release the whole block back to the operating system. So you're by splitting the memory allocation per component or per data structure, that will allow you, when the component or the data structure finishes with its job, you can return all the memory back to the operating system. The implementation of your STL allocator can be really, really simple because it has only limited functionality. The system allocator must support all possible sizes and must support the allocation, efficient, and so on. And this, with the custom STL allocator, you are adapting to your data structure, so you don't need to take care of this. So the main reason why you would ever want to use a custom STL allocator is performance. I don't see any other reasons for this. So here is an example of a custom allocator for custom allocator for the CTL container. It's called the zone allocator. And why is it called the zone allocator? Well, when it's created, it allocates a huge chunk of memory. It's one gigabyte in size. So when you ask from the operating system 1 gigabyte of memory, it just makes a reservation in some table there. It doesn't actually allocate 1 gigabyte of memory. So you're fine even if you're using just a few kilobytes. Don't worry, your program won't run out of memory. Yeah, when you destroy the allocator, you release that memory back to the operating system. Now, this is the reason why it is called a zone allocator is that when you allocate, you take a block of memory and just take the first. So there is a pointer. There is a pointer called free block index that points to the first free location in your big memory block. And when you're allocating, you're just taking that block and assigning it to giving it back. Now the allocate, which is actually like equivalent of free, it doesn't do anything. So there is nothing is done as part of the allocation. Question why? The answer is because this is a zone allocator. When we destroy the allocator, we will release all the memory back to the operating system. So using this kind of zone allocator actually makes sense if you are creating a huge data structure like a binary tree or a hash map. And after you create it, you don't change it anymore. So it will use. There is no point of implementing the allocate. Okay. Any questions until this? Until now?
There is one actually, which, as it happens, I asked.
Yes.
You were talking about the vectors of heterogeneous types and
yes.
how you might use pointers to them, and that's the problem.
Yes.
But you could use something like a stud variant or some other way of making them to value types.
Yes.
And holding the content locally.
Yes.
Would that go around the issue you're talking about of fragmentation?
Yes. The main idea is not to have a pointer to a heap allocated object, instead to keep the object in the vector itself. That's a huge help for both for the allocation, memory fragmentation, and if you're iterating through that container, you'll have much better performance.
Okay. Thank you.
Okay, one of the solutions is not to allocate objects for communication. There's a common pattern that you have two threads that are passing objects as messages. So one is allocating object and creating, and the other one is destroying. So the sender thread allocates object, the receiver thread deallocates it. In a busy system, this can make a large amount of calls to the system allocator and can create a lot of memory fragmentation. Additionally, there is a problem with the system allocators. They typically don't do well when you allocate memory in one thread and release it in another thread, because often they try to avoid thread synchronization through some clever tricks. A solution is, instead of when you allocate memory, that's fine. When you release it, don't release the chunk of memory back to the don't call free on it, or don't release it back to the operating system. So how is it done? So this is a syntax that is a bit less known. So you can allocate. You can ask using malloc, you can allocate block of memory, and then you can call a constructor on that block of memory. So when you call new without these brackets, it will allocate memory and then call the constructor. If you put a pointer to a block of memory of a good enough size, then you can call it like this. So you will allocate your object like this, and then when you want to destroy it, you call the destructor like this, but don't call free on that block of memory. Just keep it somewhere on the side that you can reuse later. And the next time when you need block of memory, instead of calling malloc, you can simply reuse the block that you stored elsewhere. This approach also decreases memory fragmentation. There's some other ideas on how to fight memory fragmentation, and all of these approaches that we talked until now both decrease the memory fragmentation and also decrease the number of calls to new and delete. One of the ways to do it is to pre-allocate. In embedded system, this is really important because embedded systems typically run a lot of time, so for a long time, and then you see the effects of memory fragmentation really, really well. So one of the ways to fight memory fragmentation is to pre-allocate all the needed memory up front. So, for example, if you have a table that has maximum 1,000 entries, you will allocate a table of 1,000 entries at the program beginning and never do any allocation there again. One of the things that they often do, for example, they did in TV box, in the job that I worked earlier, the television box development, and they restarted the program. 3 o'clock in the morning, your set-top box, television TV box restarts, and no memory. It's like restarting Windows back in the old days. So it becomes slower, and then you restart it, and it's back up at its full speed. Restarting program is not always simple. Sometimes you need to keep the data. Your program is in a certain state, so you need to have a way to maintain that state. Sometimes it's not, depending on the program. If your data structure is small most of the time, you can use something called small buffer optimization to avoid small allocation in the heap. An example is std string. So how string works? If the length of the string is less than 24 bytes, it doesn't allocate anything on the heap. And it has this clever usage by using unions to use those members that are not used when you don't have any heap allocation, then it uses to store string itself. So if you want to know more about it, especially if you have small vectors, like vector of 1 or 2, typically that will hold 1 or 2 or 3 variables, this is something that is really, really good and really good for performance, a really clever idea. So I suggest if you need this thing, you should look it up. You can also use special system allocators that promise low fragmentation. Now, not every of the presented techniques is applicable everywhere, so you need to use your good judgment and pick one that is suitable for the problem you're trying to solve. Okay, any questions until this point?
We do have one question, and before I get to that, I just want to tell a little story. Because I used to work at one of the banks, and one of the first tasks that I had when I got there was we had reports that the service we were running, which was just a logging service, was leaking memory all the time. And they actually had someone one of his jobs was, it was something like 3 o'clock in the morning. They would go and check and they'll just restart that service every day. So I was given this leak and I fixed the leak. We published a new version. The only change was it fixed the leak. Problem gone. And half the teams that were using it never picked it up because they had someone that would do manual garbage collection and restart it for them. So, yeah, try not to introduce the leak in the first place, but the restarting is surprisingly effective. Anyway, we had a real question about the zone allocator. Is zone allocator much faster than stood PMR monotonic buffer resource?
Oh, I don't know what's a monotonic, but this is just an example. So you should definitely, everything about performance is measurement. Sometimes you get really surprised by the results. So
the PMR allocators are fairly new, so it's definitely worth benchmarking that if you're interested.
How it's called? PMR.
It's PMR. polymorphic memory. I forget the full acronym actually now, but it's the new way of doing allocators.
Okay, I look it up, and yeah, it can be a fun thing to write about. Okay, I look it up. I don't know, but I look it up. This is a nice thing that you discover also new. While you're presenting, you're discovering also new content. Okay.
I'll let you carry on.
Okay. Now, next talk are off-the-shelf allocators. So these are the things that you can. There are a few good open source allocators that you can use in your projects, and there are also some closed source. Now, about the system allocators, off-the-shelf allocators that come as libraries, there is no perfect for all applications. You need to test them, and you need to test them extensively to verify them with your programs if they fix your issues. There are some things to keep in mind. First thing is allocation speed, which is the speed for both malloc and free. You need to measure the allocation speed. Second thing is memory consumption. Your program might be super fast, but if it consumes 5 times more memory, then that might be a problem. So there is some part of memory that gets wasted in each block due to allocation overhead. So every block has some block metadata that you don't see, but it is somewhere written, and this uses memory. This is important if your system has little memory, for example, embedded system. Next thing is memory fragmentation. You also want to measure that. So how does your program behave? Even, for example, it might happen that at the beginning the allocator is fast, but after time, as the time progresses, it gets slower and slower. I guess this is more important in the server settings. And also the data locality. If you have 2 consecutive calls to malloc that return neighboring memory chunks, later when you're traversing memory chunks in a vector linked and so on, this access speed will be much, much faster. So data, one thing is that maybe it's not clear, but also affects your program's performance. You can have an allocator that's super fast, but if it gives you chunks that are just scattered around the memory, that might create a problem later. It is not easy to measure all the parameters, but just measuring runtime, just to let you know how to measure them. That's a completely another story. The standard C library provides implementation of malloc and free. These are most commonly available on Linux, and also I guess Microsoft Visual C++ library comes with its own implementation on malloc and free. There are other allocators on Linux, and I also guess since they are open source, that they can be compiled for other operating systems as well. So each of the big vendors have their own. So Google has tcmalloc, Facebook has gmalloc, Microsoft has memalloc. There's also horde allocator, ptmalloc, and dlmalloc. Most of them are installable from the repositories, and each of them makes certain trade-offs for speed and memory consumption. There is no good or bad, so you need to try them, measure speed, measure memory consumption, and see which one suits your needs. Okay, now a short hands-on. The allocators, you can either, there are libraries, so you can either link against them. In the Linux environment, you can use the LD preload, this one. So LD preload is an environment variable that you can use to override the default allocator. And here is an example of how you do that. So you specify LD preload like this, and then you call your program with all the parameters. Let's test a few of the allocators. We'll test Google's, Facebook's, Microsoft, and built-in. So example is in the terminal. So here it is. I have everything ready. So this is an example. It's called from the speech processing program called Caldi that does speech recognition, and internally it allocates a lot of memory. It has a lot of calls to the allocator because it keeps its data in linked lists. So that's the way how they keep their data. That's not the best way, but that's one of the ways. So let's see the numbers. So the built-in allocator took 7 seconds to complete, and it spent 281 megabytes of memory. The next one is tcmalloc, so the Google one. It took 7 seconds to complete. and it spent 285 megabytes of memory. Let's see the next one. The next one is malloc, so the Facebook. It took 6.7 seconds, and it took 280 megabytes. And the best one, as I see here, is the malloc from Microsoft. It took 6.5 seconds, and it took 284 megabytes. So these numbers are not really representative. In this case, malloc was fast, as my computer is now under stress because it's running the streaming session. But as you can see, the way you should try it, it's really simple. So you just prefix each. So see, I'm prefixing with the library that replaces malloc and free, and you can quickly test if the allocator is worth investigating further. Okay, in this case, Microsoft was winning, and it was from 7 seconds to 6.5 seconds, but I also know that malloc and malloc are really good allocators as well, at least in this point. So, any questions until this point? Questions? Okay, moving on. Okay, we finished the topic of memory access. Now the next, the topic of performance of memory allocation. Now we have performance of memory access. I think this part is a bit more interesting, although this one, the previous one was also good. So about the memory access performance. Okay, one thing to mention. So the previous talk is all about allocation, and the allocation, this talk is about memory access performance, which is mostly related to the dynamic memory, so memory allocated through new and delete, but it also applies to memory allocated in vectors and so on. But you'll figure that out later. Your program's performance depends on the way you access your memory, and more specifically, there are two things. How is your data laid out in memory? So if your data is laid out sequentially in vectors or arrays, it is much, much better than for it to be scattered around memory, which is, for example, the binary trees, how how binary trees lay out data in memory. The second thing is need to consider is what is the access pattern to your data. Again, sequential access pattern where you are iterating through memory sequentially is much, much better than random access pattern or strided access pattern. Sequential access pattern means you're accessing element 0, 1, 2, 3, 4, 5, 6. Random access pattern is just randomly jumping around memory. Strided access pattern is when you are accessing elements like 0, 4, 8, 12, 16, 20, 24, and so on. So you're going linearly through array, but there is a stride, and there is a stride. So this is a strided access pattern. When you're talking about your peak performance, a simple abstraction of malloc and free doesn't take into account underlying hardware, doesn't cut for high performance software. So when you have your data structure and your allocator, if you keep them completely separate as black boxes, completely unaware of one another, you won't reach peak performance. You need to break this abstraction and actually merge those two things together. So the allocator, the data structure must be aware of how allocator allocates the memory. Okay. So the next question is, why does the program speed depend on the memory access pattern? So the reason is the memory wall. So memory speed is a bottleneck on modern CPUs. So CPUs are really fast, memories are slow. And as the time progresses and in the future, you will see the difference becoming even greater. So the CPUs will get faster, the memory will also get faster, but not as the same amount as a CPU would like. So CPU will typically spend around 200 to 300 CPU cycles waiting for the value it needs to be fetched from the main memory in case it is not available in the data cache. This is the time that it can do 200 to 300 simple instructions. So optimizing the memory layout can really, really bring some performance benefit. To fix this, CPU designers introduced small on-CPU memory called the cache memory. This is a fast memory. It has a really fast access time, 3 to 15 cycles per access, where the CPU keeps data it is currently using. This data is called the data set. Okay. The memory, the cache memory is much smaller in capacity. Actually, there are several cache memories. There are hierarchies of cache memories, but this is not important for our story today. Okay. Any questions until this point?
There's a couple, but there's one question and one comment. The comment is from me. I was blanking earlier on what the R in PMR stood for. It is, of course, resource. So polymorphic memory resource is PMR. And the question, which relates to a couple of slides back, I think, what is multitime?
Multitime?
I'm not sure I called that myself.
It's a Linux utility. It's a really nice Linux utility. It's a really nice Linux utility that helps you. Let me just find it. So it's a really nice, this one. So it's a really nice. Time tells you how much time does your program runs. Multi-times can repeat the experiment several times. So example, I'm repeating the experiment 2 times. And it can also measure resource usage. So it's really nice. You can install it from the repositories.
Thank you. That was it.
Okay. Okay, let's talk a bit about cache memories, data locality. So every access to the main memory begins by checking if the data is already present in the cache memory. If the data is there, the CPU can access it really quickly. Otherwise, the CPU needs to wait for the data to be fetched from the main memory to the cache memory. If the CPU doesn't access data for some time, the modified data or unmodified, never mind, is returned back from the cache to the main memory to make space for new data. So if CPU is accessing memory in the cache, the cache will keep the copy of the data there to be close to the CPU. But after some time, it will return that block of memory back to the main, from the cache memory back to the main memory. This process is called eviction. Okay. Now, here is an example of data locality with cache memory. Imagine we are performing 64 million searches on a hash set. So this is STD unordered set. There are 3 hash map sizes. Small has 32 entries, medium has 1 million entries, and large has 64 million entries. The question is, how much time do you need to perform 64 million searches? For the small hash set, it takes 1.5 seconds. For the medium, it takes 2.8, and for the large, it takes 5.9. As you can see, for the large hash set, it takes almost 4 times as compared to the small hash set. Now, question why? In the case of small hash set, currently you're accessing, for example, element that's in the hash map at certain location. There is a really large chance that you will be accessing soon. Again, the same soon, because the hash map is small. It has only 32 entries. On the contrast, the large hash set, which has 64 million entries, the chances that you will be accessing the same data again is really small. So that's there is a much smaller chance that the data you want to access is in the data cache, and this explains the difference in runtimes. This memory applies to all random access data structures. If you have arrays with random access, if you have hash maps and trees, the bigger the hash map, the bigger the array, the bigger the tree, the slower it will be. And this is the data set, the size of the data set. We say if the data set is big, then it won't fit cache, and that means it will be slower. Okay, questions?
None at the moment.
Okay. Next thing to know about cache memory is that there is a component called a prefetcher. If your program has a predictable access pattern, this is typically when you're iterating linearly over a vector of objects, not pointers, but a vector of objects, or vector of integers, vector of floats, never mind. The cache memory prefetcher is a component that can figure out which is the next data you're going to access, and then it can prefetch from the main memory to the cache memory before the CPU actually requests it. So if your program is accessing memory in a predictable fashion, you will see a major improvement in speed. Here's an example. So summing array that contains 100 million integer. If you're summing, so you're summing it and you get the same result, but you're just summing it in different order. If you're going through array sequentially, so you're going 0, 1, 2, 3, so the runtime is 180 milliseconds. If you have a fixed stride, so 0, 16, 32, 48, you'll have a runtime which is 740 milliseconds, about like 4 times slower. And if you're randomly accessing your array, so you're accessing all the elements, but randomly you get runtime which is 6,600 milliseconds. It's 30 times slower than executing sequentially. So the performance. So this is an example that's a bit exaggerated because I guess you will never access your array randomly, but it might happen. Prefetcher works with sequential accesses, with strided memory access, but it is powerless with random memory accesses. Okay, questions about the prefetcher?
Nope, none at the moment.
Okay, moving on to another important topic about cache memories called cache line. So the cache memories are divided into cache line, and typically each cache line is a 64 bytes in size. One cache line corresponds to one block in memory which has identical size. So 64 bytes in cache, block of 64 bytes in cache corresponds to a block of 64 bytes in memory. If you access 1 byte inside the cache line, the cache memory will fetch the whole block of 64 bytes to the cache memory. So first byte costs you 300 cycles. Next access in the same block of memory of 64 bytes is free or very fast. And you can, if you know that this kind of organizations, you can benefit from it. So to benefit from it, how you should do? You should organize your data so the data that is accessed together is close to one another in the memory. So if you have a class and you have two members in your class, you want to put them together next to one another. The second thing you want to do is, you know that that CPU is loading blocks of memory to the cache. You want to use the whole block of 64 bytes. Every byte you want to touch it. If you don't touch it, that is the data that is transferred from the main memory to the cache and never used. It's wasted memory, it's wasted time. So here's another example of cache line organization. So I'm summing an array containing 100 million integers with a stride. Okay. So stride 1, stride 2, stride 3, and stride 4. So for stride 1, I'm accessing elements 0, 1, 2, 3. Stride 2, I'm accessing elements 0, 2, 4, 8, 4, 6. This is an error, sorry. Okay, stride 3 is 0, 3, 6, 9, and so on. So if you're accessing, so you're summing again, summing the array of 100 million integers. So if you're accessing each byte that is fetched from the memory, the runtime is 180 milliseconds. If you're accessing every second integer in the cache line in the memory, then the runtime gets slower, 210 milliseconds. And the less cache line data from a cache line that you use, your program, the loop gets slower and slower. So you see here that with stride 4, it's 270 milliseconds. So it is, I wrote this as code. It is a sin to load data into the cache line and then not use it. So every developer that is interested in performance should know this. This is the rule. I think this is one of the most important rules when working with memory. Okay. So any questions about cache lines?
if two cores or CPUs are looking at the same piece of memory, and one of them is writing to some bytes and the other is writing to some different bytes, but in the same cache line, what happens then?
Two CPUs or one CPU?
Let's say two.
That's a bad one. If they're accessing the same, the two CPUs are accessing same cache line but different part of the cache line, this is something called false sharing, and it will make your programs much slower. So they will be like about 2 to 3 times slower. So you want to avoid this. Normally, you don't. I never found any example of this. So, but this thing I heard that they happen, and there are tools that can actually detect false sharing. I know Perf is one that can do on Intel's architecture. There are counters that can count this.
Thanks. Okay. I just had to make sure you mentioned it after my JetBrains raffle. So,
yeah.
Thanks for that.
Okay.
Yeah, I'll let you carry on.
Okay. Now, a short summary about the memory access performance. So I'm summarizing everything I said. CPU always works with simple types. It works with chars, integer, doubles, floats. There are no such things as classes, not such things as a complex number. The complex are just two doubles. From the performance point of view, dependence between how does the access speed depend on the memory access pattern? So first thing is sequential access. You're accessing neighboring simple types. So you see there is a vector of integers, and then you're summing by accessing every element. So you're accessing every element. This is the best performance. So why is it the best performance? You're using the cache line, all the data from the cache line, and the memory. There is a limited memory bandwidth between CPU, and you're using those resources optimally. Next type of access is strided access. So you're accessing a simple type in a vector of class instances. Bad for performance. So it's not as bad as random accesses, but it's bad. And the bigger the class, the worse the performance. So you see there is a vector of rectangles, and I'm now counting all the visible rectangles. Now, if the rectangle is a class, so the visible will be at offset 0, and some other will be at offset 4, and some other member will be at offset 12. So if the class has 12 bytes size, if I'm iterating through this class, I will iterate at memory location 0, memory location 12, memory location 24, and so on. So this is strided access. The worst memory access is random access, when you're randomly accessing objects in memory. So you have set, map, list, or you're accessing an object through a pointer. So this is an example when you're iterating over a set. Okay, and this is a random access. Next, you have a class car that defines the driver as a pointer, and then you're accessing the driver class through a pointer. So basically, you have here an random access memory access. Unless you have take precaution, you have a random memory access. And just reading this field can take a lot of time. Even though it looks like innocent, it's not. Okay. Now I'm going to give you a short experiment with class size and memory layout. So this is a class rectangle that we talked about, and it has three members. One is called visible, one is called point 1, and point 2. So if you think about the rectangle, it has a visible attribute, and it has a point 1, which is the left upper point, and point 2, which is a lower down point. And there is this functions called calculate surface visible that takes a vector of these rectangles, and then if the rectangle is visible, it adds it to the surface to the sum surface. Okay, so it iterates through all vectors and calculates the sum of all surfaces. So this code is accessing this visible data member, but also this P1 and P2, which is part of the calculating of the surface. Now, what we did here, we added one padding. So this is an array of integer between the ball and the first and the second data member, and also we added another padding at the end. Now the question is, does the performance of this function depend on the size of the class and on the size of the padding between the visible and P1 and P2? Okay, so let's find out. So, just a second. So this is a function called calculate surface visible, but there is also another function called calculate surface all that iterates through all the rectangles, but it doesn't touch this visible property. It only touches point 1 and point 2. Okay, because it doesn't check if the rectangle is visible. Now, the minimum class size is 20 bytes, and then we added padding and the end. We added padding at the end to make the class grow larger and larger. And you see, for the smallest class, 20 bytes, the runtime for calculate all is about 30 milliseconds. And for the worst, when the class size is 500 bytes, the runtime is about 150 milliseconds. So it's 5 times worse. Similar is for the calculate surface visible. The runtime when the class is small is about 110, and when the class size grows, the runtime gets worse, and eventually it becomes around 200 milliseconds. So it's 2 times slower. So as the class grow, iterating through it becomes slower. So next thing is to add a gap. So we added some integer. So we added some padding between the visible and the point 1 members to check does that matter. So the red one is the calculate surface all, and the blue one is the calculate surface visible. Now the calculate surface all, the runtime does not depend on the padding because we are not accessing the visible attribute. We are only accessing 2 points. The calculate surface all, actually the runtime depends on the runtime depends on the padding between visible and it's called the padding between the visible and the rectangle. So in the best case, it's 200 milliseconds, but its worst case is 250 milliseconds. This is when the class size is fixed 248 bytes. Okay, so as you could see, this is the measurement I did earlier. So it is important to have small classes, and it is important to organize data members in those classes so that the data members you're accessing together are close to one another, declared close to one another in the class declaration. Okay, any questions?
There was a question from earlier when you were talking about cache lines, but it's about alignment, so it seems appropriate here as well. It's asking, is there a way to align a data structure to a cache line boundary in memory?
Yes.
And I think maybe the question is not quite right, but there may be something in it.
Okay, so there is a way. I think C++ 11 has that structure align as 6432. In some cases, you want your data structures aligned. In other cases, you don't want your data structures aligned. So the alignment is like this. If you have a really, really huge array that you're accessing randomly, and then you're accessing, it might happen if the data structure is not aligned at which is a multiple of cache line size. It might happen that your data is split between 2 cache lines, and then you want to avoid that. But if you increase the cache, if you force alignment of the structure, that you actually increase its size. And as you could have seen, increasing the size of the class actually makes your program slower. So there are some cases when you want to do that, some cases when you don't want to do that.
Makes sense. Yeah, thank you. Okay. And there's another question that's just come in, actually, to do with calculate surface all. Says it should still depend on the total amount of memory that needs to be loaded. So more padding means more memory. The graph suggests there's no dependency. So why is that?
So the class size is fixed. So you see, the class size is 248 bytes. So what we did here, we had padding here, but we removed it at the end to make the class size.
That's what I wondered if you'd done. Okay, thank you. That clears that up. And there is another question that's just come in. Are there any good tools to visualize cache usage, etc.?
No. To visualize. So what does that mean? The best tools related to the best tools that I personally really like and enjoy working with is Intel's VTune profiler and Intel's advisor, that both can detect places when you have where your program is not efficient in detecting, not efficient in not accessing memory efficiently, but they don't tell you exactly what's the problem. So there is this company I work for called Appentra, and they're developing this tool that can not only detect but also propose fixes for this kind of situation. It's called Parallel War Analyzer, but it's not still ready. I guess it will be ready in a few months. So that can also detect, but also it can also propose some fixes how to fix those problems.
Okay. Thank you.
Okay.
Okay, that's all for now. I'll let you carry on.
Okay. So what are the principles of cache-aware software design? So one of the principles is to make data access predictable. So again, we go back to the vector of pointers. Iterating over a vector of objects is almost always faster than iterating over a vector of pointers. So we already talked about the alternatives for the vector of pointers. The reason this is true because there is no random access. When you're iterating through a vector of objects, you're iterating through, you have a strided access, which is not perfect, but it's fine. If you want a good, you should use fast access data structure sparingly. So CPU needs to chase pointers for trees. So need to go pointers and then to follow pointers, go 1 pointer, pointer 2.3 to go to find your data. Or hash maps, you should sparingly use those data structure. The memory access pattern is unpredictable and the hardware prefetcher doesn't work. Classes that contain pointers to other heap allocated class will also suffer for low performance when the pointer to the other class is dereferenced. Again, this recommendation comes with a warning. So sometimes you might want to have pointers to the other classes. Why? Because pointer, if you keep your class as part, your class, you decided to get rid of the pointer, so you moved your class inside. So you declare the class, you do not access it through a pointer, it's part of your class. Now the class is bigger. And as you've seen, the bigger the class, the slower the performance. So sometimes maybe you want to do that, but maybe you want to split your classes in two vectors, and one vector is for the class 1, and the other vector is the class that's pointed to. So then you have the predictable access. Again, don't use linked lists. I think this is the most bad. Linked lists have this really nice opportunity that you can filter out data, but there is also some vector-based alternatives that also works. For example, colony bucket array or a gap buffer. Okay, so this is the array of pointers. So this is your std vector of base class, and it has pointers to the elements of the heap. Now imagine this is one big block of memory. This is an optimal layout. If you're lucky enough that your memory allocator allocated the objects in memory in this way, then you'll get optimal performance. So you won't suffer any performance, even if you're using array of pointers. But if you're not lucky enough, or maybe you did some modification of the vectors, you deleted or added some elements, or you did it for a longer time, then you can get a non-optimal layout. So the first element points to this chunk, and the second element points to this chunk. And this is a non-optimal layout that will be slow. Okay. Any questions until this point?
No more questions just yet.
Okay. So again, I'm again talking about the array of values versus array of pointers. So this is taken from an article I wrote from my blog. So arrays of values are much better for performance compared to array of pointers. So why? All memory allocated in a single block, which means no calls to malloc and free, less memory fragmentation, sequential access to objects translate to sequential access to memory addresses. There is no virtual dispatching that additionally can slow down your program. This is not related to data caches, but virtual dispatching has its own problems. The compiler can inline small functions if you're using arrays of values, because the type of the object is known as compile time. The downside is no polymorphism. Okay, for speed, prefer arrays of values, but this is not always possible. We talked about, in the earlier slides, we talked about the alternatives. Okay, array of pointer performance. So this is an example taken from this article. There is you have a perfectly optimal layout and perfectly non-optimal layout. So in the perfectly optimal layout, the pointers in the vector of the pointers in the vector point, neighboring pointers in the vector point to neighboring memory addresses. So you have a perfect layout. And if it's a perfect layout, your program will call to a small virtual function will take 384 milliseconds. But if you have a perfectly non-optimal layout, it will take 5 seconds. So it's about 15 times slower. For a large virtual function which has many computations, the perfectly optimal layout will take 2.6 seconds, and the perfectly non-optimal layout will take 16 seconds. Now, your program will be something in between those numbers. But if you're modifying your vector and doing modification, adding, removing objects and so on, it will tend to deteriorate and become more and more non-optimal. Okay, any questions about this?
Not just yet.
Okay. Okay, principles of cache-aware software design. 2 of 4. The whole block of 64 bytes is loaded into memory. Don't let data in the cache line go wasted. Keep your classes small. So, if you have a class and you're iterating through your performance critical vector of objects, and then your class is small, you're accessing every member in the class. So if it has 3 members, you're accessing every member of that. That means that the performance, that the cache line will be optimally used. You have 100% cache line utilization, and it will be that's the best performance you can get. So data members that are used together should be kept together. Everything else should be part of another class. You want to load only data into data cache that you actually use. So data that you don't load is a wasted performance opportunity. You need to declare data members you access together close to each other. We talked about that too. This increases the likelihood that the data members will be in the same cache line. You want to keep your small classes in a dedicated vector. You don't want to process small classes as part of larger classes. So this will make things more inefficient if you do. Okay. Here is an example of memory layout if you have small versus large classes. So this is a small class. So the blue one is visible and the green one is a point member, and the orange is the cache line. So as if this is your vector, and you see how your vector transits to cache line. So the first object fits completely in the cache line 1. The second object is split between cache line 1 and cache line 2. But that doesn't make a problem because the cache line 1 is already loaded, and cache line 2 is the cache line 2, you will load it when you need it, or the prefetcher will load it for you. Now, if you have a large class which has unused memory at the end, so this is a large class. So you have a visible, and you have a point, and then you have this unused place. What happens? So the first members you're accessing are in the data cache line. The second cache, there are some things that you're not using, but small part. The second cache line, the second object is in the third cache line, and you see it's split between the third and fourth. Then you have some part in the fourth cache line, fifth cache line, and sixth cache line. So you see this is much more inefficient because you're loading, for example, here you're only using the 1/3 of the cache line. Here you're using 1/2 of the cache line. And this is the case where you have large classes with unused members at the end and also in the middle. So what happens here? You have, you see, your first, so this is one class here. So it's 2.5 cache lines in size. So one part is in the cache line, in the first cache line. The second part of the data is the second cache line. The second instance is in the third cache line, and so you're using much more inefficiently. You're using your cache lines and cache much more inefficiently compared to the previous example. Okay, and I think this illustrates the problem quite nicely. Questions?
None from Remo, but I had one, which is what you're saying here, that really what you should be doing is keep your commonly used members locally in your class and up the front, and then maybe have a pointer to, say, some less commonly used members, if you have them.
Yes. So if you need to make a difference between the code on the hot path and the code you rarely execute. You want to keep the classes in the hot path. You want to keep them small. And what you rarely execute, you can do other types of. You don't need to take care that much about that one. But on the hot class, I mean, keeping classes small also has other advantages. Small class means small responsibility. I mean, everybody's seen that code bases have like huge classes with 1,000 members. I mean, what do you do with that? What's the responsibility of that class? How do you maintain that class? We had a file that had 10,000 lines. What do you do that? When you open it, you kill yourself. Okay.
Thank you.
Mm-hmm. So, class size, data layout, and performance. So, object-oriented paradigm in C++ can be inefficient from the performance perspective because of containers of pointers that you have to use if you want polymorphism. So this is not something that you must use, but the C++ and the way the things are done in C++ actually forces that upon you. You have containers containing objects of different types. So that's also one of the problems. If you can avoid, this is partially related to data caches, but much bigger part related to the CPU efficiency. Problems of large classes, problems of classes that have members that are pointed to other heap allocated classes. So in game development, they use another paradigm called Entity Component System, ECS. What they did there is they get rid of large classes, and they get rid of inheritance completely. So you don't have like a class. They use instead of inheritance, they use composition, and each entity is just a number. For example, 1, 2, 3, 4. And it consists of components, and each component is separate. If your entity has a component in the component itself, there will be in its list, there will be 1, 2, 3, 4 as an entity, and then you know that your component has this, that your entity has this component, and you can change components in runtime. Just remove them from that table, and your entity doesn't have that component anymore. Components are processed independent of the entity they belong. This thing was really, I mean, when I first read about it, these things were really, really strange to my object-oriented way of thinking. You want your class like a thing that exists, and you have entity that exists in a vacuum. It exists of pieces that are kept in different components, and each component is processed separately. So this is maybe not the best way. This is from the readability, maybe not the best way of doing programming. But when you have a game that you want to push out to the market, it's really good if it's 5 times faster than if you do it right in the object-oriented way. And for example, the Unity engine is written using the entity component system. So I don't think the world is moving toward an entity component system, at least the regular C++ development. But there are some principles there that can be useful in programs where the speed is important. Okay, questions?
No more questions. Just an observation from me that is that basically the same as denormalizing database tables?
Yes. There is a book called Data-Oriented Design, and actually the first two chapters is actually about databases and in normal forms and denormalization. because they use that approach there. They start off from completely different point. In classes, you have an object which has properties and so on. In entity component system, you say we are the game is collection of data. We are processing data and we are organizing everything around data. Okay, moving on. Principles of cache-aware software design, 3 or 4. So since you rolled your 64 bytes of memory, you don't want the data to go wasted. So if you have a binary tree, and if it's a small binary tree that contains integers and so on, it might happen that the size of this node structure is like 24 bytes, and the rest is thrown away. So you should prefer n-ary tree implementation. So not the binary, but ternary, quaternary, and so on, because they use cache lines. These implementations use cache lines more effectively. And as an added bonus, the n-ary trees are shallower than binary trees, so it takes less pointer indirection to get to the result. And this is an added. So the n-ary tree are much faster than the regular binary tree. They can be like 2 to 3 times faster. One of the things you don't want to do is not store pointers in hash maps. So store whole objects. Having pointers in a hash map adds another cache miss because you have now an indirect access required by the pointer. So pointer is only 4 bytes or 8 bytes, so its cache line utilization is small. If you keep a whole object, the cache line utilization is much better. If you need to use hash maps in your program, there are hash maps that are based on open addressing scheme. So in case of collision, they perform better in terms of the cache misses. So open addressing cache maps, if you are interested, look it up. This is a nice concept, but it also comes with its own downsides. If the cache map becomes the load factor is too high, there can be performance problems in case there are many collisions. Okay, now let's give an example of a binary tree. So you know what a binary tree? It's a data structure used for fast lookup. You want to check if the value is present in the binary tree. You want to insert value or remove it. So here's an example of a binary tree. It's a lookup tree. So let's say example, I'm looking for number 7. So how do I look at it? This is I start from the root of the tree. I know 7 is less than 8. So if it's less, I go left. If it's greater, I go right. 7 is less than 8, I go left. Now, 7 is greater than 3, I go right. 7 is greater than 6, I go right. And here is number 7, I found it. It's in the tree. Okay. So this is the main principle is if you go left, if it's smaller. If you go right, if it's larger than the value in the current node. So how do we represent this? We use a struct which has a value left and right. Now, what is the problem with binary trees? Well, memory is one-dimensional, unidimensional. It goes from left to right, and the binary trees aren't. So what is the optimal way of laying out your data in memory to get optimal performance? How to optimally represent this memory structure in memory? And here are 3 examples of how it's done. So consider this tree here. So one of the way we can lay it out is to do it in the breadth-first search order. So first we are putting nodes on the level 0, then nodes on the level 1, and then nodes on the level 2. So you get 1, 8 on the node 0, then 5 and 11 on the node on the level 1, and then you get 3, 7, 9, 13 on the level 2. So 8, 5, 11, 3, 7, 8, 13. That's the breadth-first search in order. Another search order is a depth-first search order. Now, what we are doing is we are visiting the tree, using depth-first search, and then laying out the nodes in that way. So I'm laying out 8, then 5, then 3, then go back. I add 7, then go back, then add 11, 9, and then 13. So this is a depth-first search layout. And there is a random layout. I just randomly put them in memory. Now, question is, which is the most optimal layout? Can somebody give me Can somebody tell me which is the most optimal layout and why?
Not seeing any responses in the chat, but we do have to take account of the 10 to 15 second delay. So
okay,
we'll see if anything comes up.
Okay.
No takers by the looks of it.
Okay. So remember the main principle of memory access. What you access, you should keep things that you access together close to one another in memory. Okay.
Got a couple of votes for breadth first.
Breadth first, huh? Okay. But why breadth first?
It says because we hit the top more.
That's one of the reasoning, but I mean, you also hit the top more here. It's also start from 8. Now, the winner is the depth first search order. And why? Because if you look what happens here. So you're accessing number 8. So you're accessing number 8, the root. The left node is always neighbor in memory. So 5 is neighbor to 8, and 3 is neighbor to 5, and 9 is neighbor to 11. And this actually has a performance implication. So the breadth first search layout is better than depth first search layout. But actually, there is one even better than the depth first search. It's called Van de Bos layout. So when you're laying out your data in memory, you're laying out 1, 2, 3 close to one another, and then you're laying out 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 14, 15. Okay. So here's a look at performance. So this is a perfect binary tree. So perfectly in the sense it's how it's called in English. It's perfectly balanced, and memory is allocating using malloc on the allocator. And there are 3 kinds of allocators. There is an standard allocator, optimal allocator, which returns neighboring memory chunks if called. 2 calls of malloc return neighboring memory chunks, and there is a non-optimal allocator. As far as the breadth first search, so I don't remember the size, but I think this is a really large binary tree, so it doesn't fit the data caches. So you'll have a lot of cache misses here. If you use the breadth first search layout, the optimal allocator will be 11.2 seconds. If you use depth first search layout, the runtime will be 7.2 seconds. And if you use Van de Bos layout, it will be 6.4 seconds. So this is the best number you can get. And this, if you can see, the standard allocator is a bit slower. And it's a bit slower, but not that much. And also you find the same pattern that the breadth first search is fastest, the slowest, followed by depth first search, followed by Van de Bos layout. Now the question is, can you guess why allocator is slower, standard allocator, than compared to this optimal allocator? So let me answer that question. So the optimal allocator just allocates chunks of equal size, and it's a zone allocator. That means that there is no metadata that is related to the chunk. There is no metadata, and the good thing about no metadata is also loaded to the data cache. Even if you never access it, it's loaded in the data cache and makes your program more inefficient. As far as the non-optimal allocator runtime, you see that if the allocator is just returning random memory chunks, the layout doesn't matter that much. DFS and Van de Bos layout are almost the same, and BFS is a bit slower. Okay. Any questions?
Not for now. Actually,
Okay.
there was a question from earlier. I don't know if it's worth going back to it now about the data-oriented design.
Let's like this. We are almost.
Shall we say that?
Yes.
Yeah, we'll say that then.
Yeah, I'll stay on the room. We can chat. Okay.
Yeah.
Okay. About the binary tree example and the memory layout, when we gain performance, if we allocate a dedicated block of memory for the data structure, that means that the related data is kept in one place. There is less memory fragmentation and the better cache line utilization. If we try to keep the block of memory as compact as possible, that increases the cache hit rate. Even keeping the memory as compact as possible for your data structure actually increases the data cache hit rate. These are the numbers in statistic. If you increase it by 1% or 2%, you get like 200 or 300 milliseconds. So it makes sense to pay attention to these details. If we take advantage of cache line organization, so if two nodes are adjacent in the tree and they're adjacent in memory, there is a high probability that they will share the same cache line. If they share the same cache line, we get the access with no cache misses. We gain performance also if we keep the struct node as compact as possible. This increases the likelihood that two or more nodes share the same cache lines. On a 64-bit system, so the struct node has a left and right pointers, and each pointer is 8 bytes inside, so we're using 16 bytes of memory to keep pointers. On 64 bits, only 64-bit systems, only 48 bits of a pointer actually used. The upper are zeros. That means you can combine two pointers to decrease the size of struct node. Even if that increases the amount of work you need to extract using bit operation to extract those values, nevertheless, your program will be faster because the memory is much, much slower than the time needed to perform those calculations. One of the ways to improve the speed of your memory-bound program is to recompile it for the 32-bit system. Another way to increase the binary tree performance is not use an allocator to allocate chunks for the tree, but to use an std vector as a memory allocator. And instead of and in that case, you don't hold pointers, but you hold the indexes into the array as a left and right pointers. I hope I'm clear what I'm saying. And because you can use 32 bytes to hold indexes, that means that your struct node will be smaller. Okay. Any questions?
No more so far.
Okay. Binary tree, binary tree modification. Now, if you add or remove nodes, you slowly make the memory layout less and less optimal. After some time, the access becomes slower and slower. So what are the solutions to that? You can recreate the data structure, which is optimal again, or you can perform some kind of defragmentation on the existing data structure, but this might be complex to do. One of the ways to do is not to delete the nodes. Keep them around for some time so they can be used, possibly can be reused later if the opportunity arises. This can take time, so all these techniques can take time, but eventually they can make your long-running program fast. Okay. Now, I have a question. We are almost out of time. I have one more example, or we can skip it. So I would, Phil, what do you say?
I think we can carry on for a few more minutes. It's not a very hard deadline, as long as we're not running for hours.
Okay, so this is a hash map example. This is an implementation of hash map. So this is an example hash map that uses array to store its values. Inside each element of the array, there is a counter that, so inside each element of the hash map, there's a counter that counts the numbers of data in that bucket. And there is also a pointer that holds to the array that holds the values. So here this bucket holds one data, and there is a pointer to this one. This bucket holds 0 data, so the pointer is null. This bucket holds 2 data, so there is a collision here. The first value and second one, and so on. So what is the problem with this approach? The problem with this approach is that first you have generally you will have a data cache miss when you access the hash map bucket, because that hash map bucket is basically random access. But then you get another data cache miss when you want to access the actual data. So one of the ways to fix that is to figure out an optimized value. So instead of keeping in the vector like this, so you decide in each bucket you will keep one value, you will keep it in the bucket itself. So you get rid of the because in your optimum case, if your hash map is not full with conflicts, then your bucket will hold most of the time 0 or 1 data. So optimizing in this way is actually fine. And as you can see here, this is the approach that we take. And then when you access the bucket itself, you read this count member, but you also get this value, the object itself, you get it for free because it gets loaded as part of the same cache line. Now, how does that affect the lookup performance? So that again depends on the size of the load. So the size of the hash map. Is it 32 entries, 1 million entries, or 64 million entries? So we are performing 64 million lookups. So let's compare it. Simple hash map for the large load takes 5.8 seconds and takes 3.7 seconds for the optimized case. So it's almost 2 times faster. Not 2 times, but 1.6, 1.7 times faster. For the small loads, the difference are smaller. So as you can see here. So these things actually makes a lot of sense if the hash map is large or medium, but if it's small, it doesn't. And as you can see, if you compare the STD unordered set with this optimized hash map, it is faster. The optimized hash map is faster for the large case, but it's actually slower for the medium case. So I didn't investigate the reasons why, but that is how it is. Okay. Next principle of cache-aware software design. Don't let the data you will reuse in the future get evicted from the cache. That means don't iterate the same container 2 times. I think this is one of the biggest sins with the STL algorithm that STL algorithm library makes possible, because you want to do it, find minimum on the container, then you can call another function to find maximum on the container, and this will take time. The second thing you don't want to do if your program is for performing many random accesses, to increase the likelihood that the same data is not evicted from the data cache, you should try to decrease the size of your data structure. So any effort to decrease the size of your data structure will actually mean increasing performance. You can move rarely used members out of the hot class. You can recompile for the 32-bit system. So this makes pointers smaller, so the data structure internally becomes smaller. You can rewrite the code not to use pointers, but to use offsets from a fixed rate. So let's measure some of the things here. So finding minimum and maximum in the vector, class size is 16 bytes for 100 million elements in the vector. So if you're using, these numbers are wrong. So in separate loops, it takes 368 milliseconds. In the same loop, it takes 207 milliseconds. So if you're iterating over a container, just do as much amount of work as possible, because the memory access is expensive, not the computation. For example, here's the example of our binary tree from we talked about earlier, that's recompiled for the 32-bit system. So the 64-bit version with BFS layout takes 11.2 seconds. On the 32-bit system, it takes 9.8 seconds. The DFS layout is also faster, from 7.2 goes to 6.5. The same is the case for the one-hand Delboas layout. It goes from 6.4 to 5.9 seconds. Okay, any questions about this one?
No questions at the moment.
Okay. So we talked all the time about the optimization. Our question is when not to optimize, and there are many times that you don't want to optimize. So some of the techniques presented here will benefit only the cases with large data sets. So if you had a binary tree or hash map, make sure it's large enough before trying to optimize anything. If it's really small, the memory won't be an issue. There maybe you will have some other issues. So hash map with 32 entries or binary tree with 128 entries is not a problem. Small data set is a data set that fits level 1 cache. So on most CPUs, this is the size of this level 1 cache is 16 kilobytes to 32 kilobytes. So if your data structure is less than 60 kilobytes, let's say you're safe. Large data set is a data set that doesn't fit the last level cache. So on most CPUs, the last level cache size is a few megabytes. This laptop has a 6 megabyte size last level cache. On server, you can expect 20 megabytes. On embedded system, maybe it's 1 megabyte. Also, when not to optimize, data structures with a short lifespan also don't benefit from optimization a lot, because creating a memory optimal data structure takes more time than the average data structure. If data structure is used a few times and then destroyed, the overhead of creation will simply dominate the runtime, and you don't want to optimize that. Okay, that's it. Okay, a few final words before the end. So most of today's software is limited in speed because there is a limit in memory bandwidth, not a limit in computational resources on the CPU. Reckless use of CPU's resources can lead to software that is much, much slower than it needs to be. With careful design, you can mitigate some of these problems if the performance is important. As you, as a developer, need to be aware of the memory hierarchy in the modern computers and how to take a full advantage of it. If you're a performance enthusiast, Electronic Arts, the game developer, has its own implementation of STL which focuses on performance. The standard STL focuses on simplicity, on memory usage. So the standard STL is meant for much larger audience, not for performance audience, for performance aware audience. So there are many great ideas on how to do optimization there. So you just Google STL to find more information about it. The end. Thank you very much. Thank you very much for the talk. I hope you enjoyed it.
Well, thank you, Ivica, for an excellent talk. What I particularly liked is that you took us from some fairly basic principles at the beginning, but all the way through to some fairly advanced stuff at the end. So no matter what your background is, you can take away something from it. So the sort of talks that I like for this meetup. So thank you for that.
Thank you.
We do still have that one outstanding question about data-oriented design.
Sure.
I'll touch on that quickly. So data-oriented design is often much harder to maintain, change, and extend than the object-oriented approach. Do you have some advice on when to use which design approach?
So I myself never used object-oriented design. So I'm not a master on that topic. Actually,
okay.
So there is this book that I read. So it's called Data-Oriented Design. It's written by, I don't know what his name, but anyways, he claims, and that's a claim that we can add, that actually data-oriented design is easier to maintain because the components is split in that way. I mean, did it ever happen to you that you reuse part of your program, but did you ever reuse part of your program, but you actually didn't design for the reuse? That's a good question.
That depends on the approach you take.
That's a good question. And the guy says, I mean, it's a joke. You want the banana, but you have to take, in the object-oriented paradigm, you have to take a banana, and then you have to take the monkey, and then you have to take the whole jungle. So it's difficult in your object-oriented programming, and I mean, this is the default approach in modern software development, is that sometimes it's really difficult to just extract one component and use it elsewhere if you didn't plan for that.
Yeah, and there are design principles around that, of course. We're opening a whole other can of worms, so another discussion. But yeah, thank you. And talking of thank yous, seeing lots of them in the chat, so your talk was very much appreciated.
Okay.
So thank you. I hope you'll stick around to talk to us in Remo as well.
Okay. Thank you, and talk to you in Remo. Bye.
Thank you, everyone.